be presenting to you Lab 3, Black Hole. So here are the contents of this lab today. I'm going to get into a lab introduction, and then I'll follow that up with the code modifications I made according to the fundamental concepts, as well as some data analysis and a conclusion. So the purpose of this lab is divided into two parts. The first part being to find the mass of a black hole by analyzing the motion of a star in orbit. And part 2 uses a computer model of the orbit to find an initial velocity required for this spaceship to leave the system without crashing. Some fundamental concepts here, we'll be using especially the momentum principle or Newton's second law and the Newton's law of gravitational force. A brief overview of the results here. I found the black hole's mass to be 1.77 times 10 to the 34th kilograms. And the initial velocity required for the spaceship to get out of the system is shown here, this number in the vector. Looking more into the fundamental concepts, we have gravity demonstrated by the gravitational force equation, and then parallel and perpendicular motion is important to this lab as well. It's demonstrated with some pictures here, and it shows mostly the breakdown of force into perpendicular component and a parallel component. Gravity is the force that attracts a body towards another physical body having mass, and the whole concept of parallel versus perpendicular forces is derived from the momentum principle, and it introduces another coordinate system with p hat and n hat, which will be explored as the x coordinate and the y coordinate in this lab. And finally, acceleration is directly proportional to force, which is Newton's second law reworded, and force is defined as the rate of change of linear momentum. So for part 1, here are the system and surroundings and the initial conditions that I'll be using and plugging into the starter code in order to derive a mass of the black hole. The mass of the black hole was found to be 1.77 times 10 to the 34th. And this was entered into the starter code for part 2 to begin calculating the speed required to leave the orbit. So this is how my part 2 starts, plugging in that mass once again. And these parts of the code were edited to show this, to show the breakdown of momentum into vectors and to demonstrate what equations are shown there. Here, the momentum principle is applied, and these formulas were derived from Newton's second law. They show the position update formula and the velocity update formula, essentially. So these are the results of part 2. The planet's orbital speed is shown here, here, and the ship is now 1.6514 times 10 to the 11th meters away from the black hole, meaning it successfully left the orbit. Some possible sources of error within this lab are error due to rounding. The scenario could be inaccurately represented due to some rounding or some approximation that I did throughout the lab or throughout the modeling of this lab. And this experiment does not account for any other forces when realistically there will be multiple other forces acting on the system. What does it mean? Well, mathematically, rate of change of momentum and net force are mathematically the same, but in this instance, it is easier to think about it as the derivative of momentum because these figures are easy to obtain using what we know, which is the change in motion, whereas net force would require having to add a bunch of forces. And finding the net force would be much more challenging. For this part, asking what initial velocity the spaceship would need in order to orbit around the black hole, I was unable to find this, but what I know for certain is that the initial x component would have to be negative and the y component would have to be positive.